Hi there, thank you for clicking on this video. This lesson is going to take us through some of our operations on polynomials. In this lesson, we're going to focus on adding, subtracting, and multiplying, and we're going to save division for its own lesson and video. Please give this video a like if you find it helpful. Subscribe to the channel for more no-frills math content. If you've watched several of these videos, you know there's not a lot of graphics or audio, but I hope what you're finding are clear lessons that help you understand the math concepts behind what you're doing in your math class. And then check out the practice set for this lesson so you can see how well you're understanding what we're covering. We're going to start with adding and subtracting, and hopefully if you're watching this as an Algebra 2 student, you have some background in this. I know I have on the channel an Algebra 1 version of this, which really introduces the concepts and keeps the polynomials fairly simple. In this one, because this is geared more for Algebra 2, we're going to build on that. We're going to make the polynomials a little messier with all of the operations, but the idea behind them is the same. Essentially, adding and subtracting is combining like terms. And just so we're all on the same page with what we mean by that, combining is kind of a blanket word for adding and subtracting. In math, when we talk about combining, we are not referring to multiplication. And then like terms are terms with the same variable part. Okay, so that's a little bit of vocabulary if you're not sure about it. Remember that subtracting is just adding the opposite. And my students that have me in class know that I say this a lot because I talk about my own math background and how I was taught Algebra 1 and how certain concepts were just really emphasized. So I want to take a moment and just look at like this idea of adding the opposite. And what most of you are familiar with from middle school somewhere where you first start to introduce negative numbers is it's a little jingle or phrase. I'm not a fan of it, but it's keep, change. Okay, not a big fan of it, but I mean, essentially what it gets at is this adding the opposite. And so if you had something like 7 minus 5, instead of looking at it as a subtraction where you're subtracting a positive 5, you would look at it as adding, and then you would say, okay, what is the opposite of positive 5? Well, that would be negative 5. And so 7 minus 5 could be written as 7 plus negative 5. And so we have this idea of like that subtraction is really just adding the opposite. Now, if you made it like a little bit messier and you had 7 minus negative 5, and that's very uncomfortable because we've got these back-to-back negatives and you're almost like not sure, should I keep them at the same level? Do I bump this one up a little bit? Like, do I put parentheses around it? And I think a lot of students do get confused by that or very uncomfortable with it because it is uncomfortable to have like the back-to-back negatives. But what we have there is 7 minus negative 5. Well, if subtraction is adding the opposite, then I'll start with the 7. I'm going to change that subtraction to adding, and then adding the opposite. We ask ourselves, what is the opposite of negative 5? Well, that is positive 5. And that is the essence of what we're doing when we're subtracting. We don't teach it like that in first grade because first graders don't know what negative numbers are. They're very abstract, like how can you have less than nothing? But as we get older, we're able to see that negative numbers might represent gaining and losing. So if you're like on the football field, if you're moving in one direction, it's positive. If you're moving in the other direction, it's negative. So we're able to handle that, and then we kind of come back and revisit that. And you can probably see the keep, change in there, but you would never hear me teach it that way. So I would always say subtraction is adding the opposite. Now, how does that work for groups of things? So in a group, you might have group 1 minus group 2. Okay, so 2 groups of things. And what you are essentially going to do is you are going to take group 1 and add the opposite of whatever group 2 is. Oops, there we go. 2. So what might that look like? Now, here's group 1, and I am going to subtract group 2. Okay, so here's group 1 right here. I am clicking something on my pen that is causing a pop-up to come up there. Okay, and there's group 2. So what we're going to do is take group 1 and we're going to add the opposite. Now, because we are adding the opposite of the group, we have to take the opposite of everything in the group. So we say, well, what is the opposite of 2x? Well, that would be negative 2x. And then we ask, what is the opposite? Remember, we're adding the opposite. So we say, what is the opposite of negative 3? Well, that is positive 3. And so we'll just add the 3. And that's how we can turn a subtraction problem into an addition problem. Now, well, let's go through a couple of examples, and then I'm going to post a link to a video that can make this very concrete for you using algebra tiles if you need it. All right, now one thing I want to say about the adding example here is these parentheses are what I call cosmetic. I use that word when I'm teaching. I say they are cosmetic, and I usually ask my classes, what do you think of when you think of cosmetics? And most people will say something to do with makeup. You know, you have the cosmetics counter or the cosmetics department. Not that most of us go to department stores anymore, but we just go to Amazon. But I think you know what I'm talking about. And if you think about cosmetics being makeup, they change how you look, but they don't change how things work. Okay, so you can put all kinds of eye makeup on your eyes, and you can really change the appearance of your eyes, but you don't change the function of your eyes. That's what these parentheses are when you're adding. They change the appearance of the problem, but they don't actually change anything operationally. The parentheses here are merely to set apart one polynomial from another. So we have one group and then we have another group. But what we're really going to do is just combine them all together into one big happy group. So a lot of times what I will recommend that my students do is that they simply remove the parentheses. Okay, and so they don't serve any function other than to visually separate the polynomials, so we can say, oh, polynomial 1 and polynomial 2, but polynomial 2, but they don't affect what we're going to do. Now, what we are going to do is combine the like terms. So we're going to go through and find like all the x to the fourths and all the x to the thirds and all the x squares and combine them with each other inside their groups. So I can find like 3x to the fourth, and then this is like a plus negative 6x to the fourth, or you could think of it as minus 6x to the fourth. Well, 3 minus 6 is negative 3, and so I have negative 3x to the fourth. And then I might go and find another color. And now I'm going to find the x to the thirds. Well, I only have one of those. And so I'll have minus 2x to the third. And now I'll find my x squareds, and there they are. And there's nothing to combine that with either, so that just comes down. That's plus 2x squared. Now I think they get a little bit more interesting. Now we have negative 4x plus 4x. Well, negative 4x plus 4x is 0, so that term actually drops out, and that leaves me with last but not least, positive 3 minus 7, which is negative 4 or minus 4. And you can see I circled everything there. You don't need to do that, but quite frankly, if it's a big problem with lots of terms in it, I would at least recommend kind of crossing off the terms as you combine them, because it's very easy to miss one. Just if your eye is scanning over a decent list there. You won't see anything much worse than this. Most of the polynomials that you will need to add or subtract will be smaller than this, except maybe when you are in a unit on polynomials, and then you kind of stretch it a little bit more. All right, so let's take a look at a subtracting example. Now, this is where the parentheses are not actually cosmetic. Now, I guess the first one is this polynomial. This just stays the same. So if you think about our keep, change, okay, like the first term in that, just you keep it, okay? It doesn't change. It doesn't have any sign flip on it or anything. So we could just remove those parentheses there, okay? We could just remove them. They are not doing anything for us. Now, here's where it gets more interesting, though. We are subtracting this entire group. This set of parentheses actually is doing something because it tells me what exactly I am subtracting. And so it's telling me, what do I need the opposite of? Well, I need the opposite of everything in here. So we can set this up as an adding problem, and we are going to add the opposite. So what is the opposite of 2x to the third? That would be negative 2x to the third. What is the opposite of negative 4x squared? That would be positive 4x squared. The opposite of positive 2x is negative 2x, and the opposite of positive 3 is negative 3. And now we're okay. Now, there's other ways that you can think of this, other ways that teachers can express it. So I'll kind of go through over here just, okay, so we have a group and then we have another group. Okay, you could think of it as distributing the subtraction, which is honestly how I think of it. I think that subtraction needs to get distributed through that whole second group. A lot of students like this. They like to picture like a -1 out in front, and they like to think of it as distributing a -1, which also works because the subtraction is the negative, and then like you have a 1, you can multiply 1 by anything. So that's a very popular way of thinking of it. How you think of it doesn't matter so much as that you've got a reliable way that is reliably giving you the correct answer, which is why I strongly encourage you to do the practice set, because you can watch this video and be like, oh yeah, like I got it. You know, what she said made sense. But maybe not. So you want to just check to see whether or not you really are understanding it. All right, coming over here, we have 4x to the third minus or plus negative 2x to the third. So that's 2x to the third. I have oops, I see where, here we go. That was x squared. Glad I caught that. Okay, we have a positive 3x squared plus 4x squared. So that's going to give us 7x squared. We have negative 2x minus 2x. Now be careful with that. Negative 2x minus 2x. That's negative 2x plus negative 2x, which is negative 4x. That's where that adding the opposite might come in like handy in terms of how you're picturing things. So that is minus 4x, and then we have this lonely minus 3 out there. Okay, so there we go. So there's our subtracting example. Now, need some extra visuals for this. Algebra tiles work well for smaller polynomials. They don't work well past quadratics, but they do work really well for smaller ones, and they can help you create a mental model for what we're doing when we add and subtract polynomials. So I am going to link a video up here if you feel like you need it. Okay, I'm going to put it up there, and so it's probably there now, but you can go take a look at that, and it's going to work through a couple of examples from a practice set. You don't need to have the practice set, but to see how you can use algebra tiles to model the adding and subtracting. So it's a little bit of an extra resource for you. So let's talk a bit about multiplying. We are going to use the area model for multiplying, okay? So that is the model that you can expect me to demonstrate. The height and width of the rectangle are the two polynomials being multiplied. So if you think about like you have base times the height, and that gives you the area. This is going to be polynomial 1, and this one's going to be polynomial 2. Okay, and then the area is the product. Okay, and so the area is the product or essentially our answer. So we're going to be looking for the area inside the rectangle. There are several advantages to structuring the problem this way as opposed to doing repeated distribution in a linear format, which is how I was taught. I was taught to do repeated distribution, which is essentially what the area model is. It's just how you're laying it on the page. First of all, it's going to be a lot more compact. You are not going to stretch your problem all the way across your page, which is really nice. It also places like terms near each other, very often on the diagonals, although that's not a guarantee. Where when you distribute in a linear format, your like terms are not next to each other. So that's a definite advantage. So here we go with our first example here. So this is a trinomial times a trinomial. And so we're going to set up our area, and we're going to use our two polynomials as the base and the height. So I'll have x squared plus 3x and then a negative 4. And then on this, for the height, we'll have negative 2x squared plus 3x and plus 2. And essentially what we're doing is we're going to find all 9 areas, and then we'll add up all 9 areas, and that will be the area of the whole thing, or our product. If you do this in a linear format, you will notice that it is exactly the same thing that we're doing. We're just putting it on the page in a different format. So we're laying it like half horizontal, half vertical instead of horizontally all the way. And we're also conceptualizing it using area. Okay, so we're tying in some geometry there. So right here we have negative 2x to the 4th. This will be negative 6x to the 3rd. And if you're wondering where is she getting that, I'm doing the base times the height of each rectangle. So this one has a base or width of 3x. The height is the negative 2x squared, which means the area here is negative 6x to the 3rd. Negative times the negative is going to give me positive, so this will be positive 8x squared. Going down to the next row, we'll have 3x to the 3rd. Then 3x times 3x gives me 9x squared, and 3x times negative 4 is negative 12x. And now the bottom row, 2 times x squared is 2x squared. Then we'll have 6x and then negative 8. Now, the answer to the problem is the area of the entire thing. And so what we want to do is add all of these little areas up. But note that the like terms are on the diagonals. So if you want to find your x cubes, notice where they are. They are literally on that diagonal. They are not scattered all over the problem. Here are your x squared right on that diagonal. And here are your x's right on that diagonal. And that will happen. Well, we'll talk about when that happens. But that makes it very easy for you to add them up because like they're already aligned. So negative 6x to the 3rd plus 3x to the 3rd is negative 3x to the 3rd. Now for this one, here's what I would do. I would do 2 plus 8 is 10 because 10 is a nice number. And then 10 plus 9 is 19. So it's 19x squared, and that's a little bit easier than doing like 2x squared plus 9x squared is 11, and then doing 11 plus 8. I mean, you're going to get 19 either way, but 10s are nice. In the x's, we have like negative 12x plus 6x, so that'll be negative 6x, and then the minus 8 is by itself. Really, I'm a huge fan of this. It is not how I was taught to do it myself, but like since I've been doing it this way, it is just so much nicer. I don't always do it when I have a binomial times a binomial because I can do those usually without showing any work. But if I have bigger polynomials, this is so much more compact. I do have a video on the channel that kind of compares and contrasts the area model with repeated distribution. So you can see like, oh, they're the same things. So if you want to do this out and you have that big, long, like line that stretches out, what you should notice is that these are the same 9 terms. Okay. All right. Now, this nice feature of the diagonals, this is going to happen as long as the polynomials are in standard form and there are no missing terms. Standard form means that your exponents are counting down. So we have 2, 1, 0 there. If they were jumbled up, then it would jumble up the like where they are in the rectangle. So they have to be in standard form, and you don't want to skip any. So you don't have any missing terms. We're going to take a look at that on the next slide. So in this one, I have exponent of 2, exponent of 1, and then the constant. In this one, I have an exponent of 2, but notice that the x term is actually missing. Okay, so there's no like something with the x in it, and we're jumping down to the constant. And that is going to change how this ends up looking. Now, you don't have to, if anybody's wondering, like, oh, do you have to do the base and the height that way, or can you set it up another way? Remember that multiplication is commutative. The area of the rectangle is the area of the rectangle, regardless of which one you make the base and which you make the height. So here we have 3x squared times x squared, so that's 3x to the 4th. Here we'll have 6x to the 3rd minus 1x squared, or just minus x squared. Now we have 9x squared plus 18x minus 3. And once again, I want to add up all those areas to get the product. Note that when terms are missing, the like terms are not on the diagonals. That's because when you leave out the term, you're actually leaving out like boxes that like would be there. And so those, like when those boxes are like taken out, like everything kind of shifts over a little bit. And so they're not on the diagonals. Now you could resolve that by putting zeros in those positions. Here's what I mean by that. So you could, do this where you have like 3x squared and then 6x, and then do x squared plus 0x and then a 3. And what's going to happen is you're going to end up with like a row of zeros in here. Okay, but it would like shift everything over a little bit so that like now they would end up on the diagonal. So just like a little caution there. Let's go ahead and add these up. So we've got 3x to the 4th. Now this, I'm just going to do this just to make sure I don't miss anything. Now I have a 6x to the 3rd. Now 9x squared minus x squared is 8x squared, 18x, and a minus 3. So just like a little bit of a caution there. It still works the same way as the last one, just yeah, if you're missing some stuff, or if somebody jumbled up the order, it would. Now, the better you can multiply using this method, the easier division will be. And I am a huge advocate of dividing polynomials using this model. If you do repeated distribution, there is no division that like works the same way. So if you do the repeated distribution, when you get to the division, you actually have to learn a whole new algorithm. You have to learn a completely new process. If you learn how to multiply this way, then we use the same model to reverse the process, and you already know what the model is. Okay, and that's a future lesson, usually the very next lesson. Okay, which at the time of recording this, I haven't recorded it yet, but maybe next weekend. I am in the throes of the first marking period at my own school, and so weekends is like the only time I can do this. So, all right. So don't forget to give this video a like and the channel a subscribe if you found the lesson helpful for you. Drop a comment or question to engage, and be sure to check out that practice set for this lesson to check your understanding. I hope to see you in a future video.